Okay, can you hear me?
Yes, indeed.
All right, thanks for your patience. Seems like there's always some problem or another, but seem to be past it now.
It's all good. And Philippe, if you can signal when you've started recording, let us know. All right, we're live.
Okay. Great. So, I think last time, oh, got to get the pen going. One, 1 second. I think last time 0%. Excellent. All right, I'll just talk for a few minutes and it'll get a charge. It's quick. Sorry for the lack of prep. Last time we saw the Sumcheck protocol, how it works, and kind of sketched how you would implement the prover quickly. Um, and I just say at a high level, it's often hard to convey like why this protocol is so useful. Um, but I sort of found the most effective way to think of it is that it it's very lightweight for the prover because there's no cryptography, and it's often confusing. People get confused what I mean by that. So it's information theoretically secure if run interactively, which is certainly one way to formalize there's no cryptography, right? There's no like hash functions that if the cheating prover could, invert or find collisions of, then it could, trick the verifier. Um, there's no cryptographic groups used where if the cheating prover could find discrete logarithms, quickly, then it could trick the verifier. So there's none of that. And it's not so much that snark designers care about information theoretic security, because as soon as you apply fiat Shamir to make things non-interactive, you're stuck with uh, computational soundness anyway. But the high level message is cryptographic operations are expensive for the prover. Just hashing data is slow. Doing group operations is slow. And so the Sumcheck protocol is like a way for the verifier to offload a bunch of work to an untrusted prover without bringing in this cryptography. So when the Sumcheck protocol is used in Snark design, the cryptography is there, and it's coming in two places. One I just mentioned is fiat Shamir to make things non-interactive. The other is in a Snark setting, the prover would typically cryptographically commit to some kind of witness, and then use the Sumcheck protocol to prove that the committed witness is actually a valid witness. And so, in Snark applications, the Sumcheck protocol does not let you totally avoid cryptography, and there's actually good reasons to, believe that there's no way to get a snark without cryptography. Um, but it does let you kind of minimize its use. So, you commit to the minimal amount of data, do the minimal amount of work to prove that the committed data is what it's supposed to be. So that's the high level idea. So the prover in the Sumcheck protocol like just does field additions and multiplications, and like doesn't and in particular doesn't do that many of them. And that's just much faster than if it had to do a ton of group operations or hashing and things like that. And so detailed performance comparisons of provers is a whole, it's very complicated. There are many things to think about and consider, and snarks are still pretty complicated. But that is just the high level kind of first order approximation for why the Sumcheck protocol is so useful. So today, now that my pen is charged, I mainly want to just cover, like, basically do more practice applying the Sumcheck protocol. So I'm just going to cover some applications. And so these are the problems I think I'll focus on today. They are covered in chapter 4 of the book. They tend not to be the most important in Snark design, with the possible exception of matrix multiplication, which actually I think is really important, especially in ML applications. But I'll start with a problem called triangle counting, which Snark people don't really care about, although computer scientists in general do. Then we'll move to matrix multiplication. And consider these are the main things I want to hit. I might cover maybe a interactive proof. Maybe I'll an interactive proof for any small space computation. Maybe these will be the things I'll try to hit. This last one is a little bit sort of will seem a little abstract or technical, just because like modeling small space computation is a little bit annoying. You need to talk about like Turing machines or something, and so if you're not already a computer scientist by training, like this might be a little too abstract for you, but hopefully I'll convey the main ideas anyway. And triangle counting and matrix multiplication are very concrete. So let me basically just dive into them. Maybe I'll just pause and see if anyone wants to ask any questions about the SumCheck protocol. Ask me to review anything real quickly about it. Yeah. Okay. Can you confirm you can hear me?
Hello? Can
Hi.
you hear?
Oh, question. Good. Okay. Go ahead.
Yeah, sorry, it was Mike. And uh, I wanted to ask about these applications of SumCheck. The particular thing, am I getting this right, that it will be useful when the problem that we have uh, suggests that we have this efficiency in summing overall all the inputs. I'm sorry for bad formulation of the question. It is related to the previous session, the last one, where I guess you mentioned it, and I'm just trying to digest this approach, this information.
Yeah, no, it's a great question, and it's exactly the answer to the question is sort of exactly why it's so useful to see several examples of applications. So, as a reminder, the point of the SumCheck protocol, what it lets you do is it lets you efficiently compute, the sum of the evaluations of some n-variate polynomial, where the inputs being summed over is 0, 1 to the n. And from the verifier's perspective, it reduces computing the whole sum to evaluating this polynomial g at a single point, for a single r. Of course, r is in sort of the whole field, whereas the sum is over points in 0, 1 to the n. But still, this is just 1 point, while we're summing over 2 to the n points here. And so it's directly useful for problems that can be written in this form, where the verifier can evaluate g at a single point quickly. That's the ideal situation for making the SumCheck protocol useful. Okay, what's the reason it's helpful to see several applications of it, and the reason I'm covering this content today when we won't really directly use it in the snarks we see kind of later in the study group, is that it takes a little bit of practice to realize that basically anything can be cast in this form. So it's helpful. Yeah. So that's what we're going to discuss today. So this is the problem that SumCheck solves, but you need some cleverness to realize that this problem actually captures like almost anything you could ever want to solve. Does that make sense?
Yes, yes, and that's why I asked that question, and that's what I want to keep an eye for to just grasp how do you do it.
Yeah, yeah. So you should keep asking, after each application, to the extent that the application itself doesn't sort of make everything clear, I guess. But there's kind of no substitute for just seeing more and more applications of it.
Thank you.
Other questions?
Let's see if wants to come on stage. But what happens when we consider ring extensions instead of extension fields in the SumCheck protocol?
Yeah. Great. So I guess the question is like what if G is like an n-variate polynomial over a ring instead of a field? Um, and so, but just for context for the whole group, a field is something you can like add, subtract, multiply, and divide in. A ring you might not be able to divide in, and in particular, you might have non-zeros A and B that multiply to 0. So those are called divisors of 0, and divisors of 0 are like one reason you can't always divide by anything. And so it's a loaded question. There have been like multiple papers on this topic, but roughly speaking, soundness can be an issue. Okay, so some of the papers talk about what's called an exceptional set, subset of the ring, where rather than so let's say, we're in the standard SumCheck protocol over field, rather than choosing, I'll try to keep this short, rather than choosing challenges, random verifier challenges from the whole field, from the whole ring or field or whatever, you would only choose challenges from an exceptional subset of the ring. And if I remember right, an exceptional subset, I think, is, it's such that for any 2 points in the set, I'm going to get this wrong. It's something like their difference is invertible or something. Like you can divide by their difference. Basically, like divisors of 0 are some kind of problem. I've never thought it through carefully myself for soundness, and at least known analyses of soundness. And that can be a big issue because I think a lot of rings people would like to work over. The size of exceptional subsets of the ring is too small or something. But so I don't think there have been too many prominent deployments or anything of SumCheck over rings yet. I will mention the latest version of the Frey-Binius paper has a very important application of SumCheck over a ring. They call it the ring switching protocol. But the ring they use, firstly, it has a field, a 128-bit field as a subset. So this particular ring turns out to like kind of act like you just choose the exceptional subset you use is a field. So so this thing is like basically not an issue. And secondly, the authors of Frey-Binius has mentioned to me that they've got another update to the paper coming out soon where they just get rid of the ring completely. So don't quote me on that, but I think that they've indicated that's happening. So as a result, I think as of today, running SumCheck over rings, has not had like a big impact. But people have certainly looked at it, and this is the main thing to be aware of, is that soundness gets tricky because divisors of 0 are a bit problematic. So I'll just leave it at that.
One more question regarding the same. Hello, am I audible?
Yeah, hi. We can hear you. Go ahead.
Yeah. In the Frey-Binius protocol, is the witness from the subfield of the ring, or is it the witness is over ring itself?
Yeah, that's it's from a like a subfield of the ring effectively. So it's sort of like, it's kind of barely using the ring already. And then I believe just going to cut the ring out entirely in a new update. But it's sort of, the ring is there, but it's like barely, like everything happens in like subsets of the ring that are actually a field roughly. I'm waving my hands like crazy here. So yeah, I think morally, they moved to rings but didn't fully exploit the rings, and because they didn't fully exploit the rings, they just circumvented, all of the issues that prior works trying to use rings have encountered, and then ultimately the ring isn't even needed. So yeah, I think, that's maybe the most I can say about it right now.
Yeah,
The
thanks.
ring is, yeah, I should maybe the ring is like, so elements of the ring are 250. Sorry. Elements of the ring are 128 squared bits. So it's a huge ring. Huge ring. Doing right? Is it so each row is so it's like it's 128 squared bits. So it is a huge ring, but again, like almost everything is happening in like, the ring has size like 2 to the 128 squared, but almost everything happens in like certain subsets of the ring that only have size 2 to the 128. So, yeah, ultimately, I think, the ring will go away, and we maybe I shouldn't have even brought it up. Great. Other questions?
I think that's it for now.
All right, great. Thanks for the questions. Okay, so yeah, let's talk about triangle counting, and then use the SumCheck protocol to give an efficient interactive proof for the problem. So to define this problem, I do have to introduce the notion of a graph. And so a graph is just a collection of vertices and edges connecting vertices to each other. So like this would be an example of a graph. It had 1, 2, 3, 4, 5. So it has 5 vertices. Vertices are just, depicted as dots, and 1, 2, 3, 4, 5 edges, I think. If I'm counting right, 1, 2, 3, 4, no, 6 edges, 6 edges. So any edge just connects two vertices. And triangle counting is the following. Given a graph with n vertices, determine the number of triples of vertices that are all connected to each other. So such that A is connected to B, B is connected to C, and A is connected to C. So that these are all edges. Right. So, to give some examples, if these 3 vertices, form a triangle because they're each connected to the other 2. Like each one of them is connected to the other 2, right? But let's say these 3 vertices do not form a triangle because this edge is missing. These 2 are not connected to each other, and so it looks like this pink one. If my brain is really not working today, but I think this pink thing is the only triangle in this graph. That is, you can look at any 3 vertices that are not these 3, and they won't all be connected to each other again, unless I'm just there's a triangle I'm not seeing. So yeah, that's the counting triangles problem. This actually comes up a lot in analyzing social networks. On Facebook, the vertices would be like accounts, and the edges would be like friendship relationships. Like if Alice and Bob are friends with each other on Facebook, that's like an edge between, those two vertices. And then a triangle would be like three people that all know each other. And like a nice way to formalize or model the problem is to talk about what's called the adjacency matrix of the graph. Okay, so this is an n by n matrix. So there's a row for each vertex and a column for each vertex, right? And the ijth entry of the matrix is 1 if, ij is an edge in the graph. So here we're kind of labeling each vertex in the graph by, a number between 1 and n. And we say that there's an entry in row I and column j if vertex I and column j are connected by an edge, and otherwise aij is 0. All right, so just as like a smaller example, here's a 4 vertex graph, and so its adjacency matrix would be 4 by 4 matrix. Let's label the nodes this way. And so, 1 is connected to 2, 3, and 4. So the first row looks like this, indicating that node 1 is like not connected to itself, but is connected to all the other nodes. Node 2 is also connected to all the other nodes. So its row looks like this. Node 3 is also connected to all the other nodes, so its row looks like this. And then node 4 is connected to 1 and 2, but not 3, so its row looks like this. So this would be the adjacency matrix of this graph, so that this matrix is A for this graph. Okay, and then once with that notion of adjacency matrix, kind of out of the way, the number of triangles in the graph is just the following. So sum over nodes I, j, k of a, I, comma, j times a, j, comma, k times a, I, comma, k. And here I'm assuming that, like the edges are undirected. So if like 1 is connected to 2, then 2 is connected to 1. And that tells you that, aik equals a, ki. Like if I is connected to k is connected to I. So it doesn't really matter whether I write ij or ji here. And yeah, so this is, summing over all triples of nodes, of vertices. I use the terms nodes and vertices, synonymously. So we're summing over all triples of vertices and asking, is every 2 nodes in the triple connected to each other, right? So, if ij and k are all connected to each other, then this will be 1 times 1 times 1, and you'll get 1. But if there's an edge missing, if I is not connected to k, then aik will be 0, and the ijk term will be 0. And so this is like asking, aij times ajk times aik is sort of asking, it equals 1 if ijk form a triangle, and 0 otherwise. And so we're just summing over all triples of nodes and ascertaining, like, do they form a triangle or not here. Okay. So questions about the counting triangles problem?
Oh, just a question about the matrix drawn above on the
Mhm.
3rd row.
Yeah.
It seems like okay, so number 3's connected to 1 and 2, but it doesn't seem connected to
Oh,
4.
thank you.
Based,
Yeah, thank you. You're totally right. I just looked at the graph wrong. You're right.
okay,
Thanks.
yeah, it was a small detail. Okay, thank you.
Yeah. Let me know if I make mistakes even when I'm not sleep deprived. So yeah, you're totally right. Thanks for catching that. Other questions? Okay. Great. So now we're going to use the SumCheck protocol to solve this problem. But before we do, like, let's briefly discuss like how what if there was no prover, right? Like, what if the verifier was just going to solve the problem on its own? Like, how fast could it do it? Okay, and there's sort of a naive algorithm. So we're not talking about so no prover. I'm just discussing like how fast is it known, solutions to this problem. How fast are they? So the naive algorithm will directly compute the sum. So it'll just iterate over every triple nodes and see, is this a triangle or not? If yes, increment the sum by 1. If no, move on to the next triple. That takes n cubed time. Okay, and there's a smarter algorithm which takes what we call matrix multiplication time. Okay, and I'll explain that algorithm in a second. But I think we discussed this when we discussed Friedwald's protocol, several weeks ago. The fastest known algorithm for matrix multiplication today runs in time like n to the 2.38 something. I don't know the exact exponents. And it's also totally impractical. And, generally, we don't expect, I think most people don't expect order n squared. Like it might, this exponent might get really, really close to 2, but it's never going to get, to be literally, a constant times n squared. So the message here is, if the verifier had to solve the problem on its own with no prover, the fastest there's no way it can run in n squared time. This is the time required, like just to read. So time to read the graph, the adjacency matrix A. It's an n by n matrix, so there are n squared entries. So basically, n squared time is linear time. It's like the fastest you can hope for this problem. It's the time required just to read the input. And we don't expect that there's an algorithm that actually runs in linear time for this problem. Possibly you can get fairly close to linear time, but you can't actually get all the way to linear time. Okay. And so in our interactive proof, our verifier will run in linear time. Okay, so the verifier will be saving work compared to if it didn't have access to a prover. So this interactive proof will be useful for the verifier. It'll save the verifier work. Okay, let me just briefly summarize this matrix multiplication based algorithm, because our second, so I'm good. This algorithm will become relevant in a few minutes. Like, it won't become relevant in our first interactive proof, but it will be relevant to I'm going to give several different interactive proofs for this problem. So this matrix multiplication based algorithm, like what it does is, first it computes the matrix A times A, also known as A squared. Okay. And if you look at the ijth entry of A squared, this turns out to equal the number of nodes k, such that I is connected to k and k is connected to j. Right. So the entries of A squared, if you they're sort of counting like length 2 paths, right? So if we have, I is connected to k and k is connected to j, and I is also connected to k prime and k prime is connected to j, that then the ijth entry of A squared, would be like 2. And so it's not hard to see if you if you just believe me about what is the ijth entry of A squared, that the number of triangles in the graph is the sum over all pairs of vertices ij of A squared ij times aij, right? And so what's going on is, for if you look at a triangle, well, what I want to say, I don't want to say this. It's like, okay, this is counting the number of k such that I is connected to k and k is connected to j. Okay, and so that these are edges. Okay, and so for each of those k's, you get a triangle if I is also connected to j. So this tells you, is I connected to j? Right. And so, for each of these k's that are being counted by A squared ij, it sort of, leads to a triangle if and only if aij is 1. And so, by summing over, the entries of A squared, but multiplying each entry of A squared by, the corresponding entry of A, you count the triangles, right? You sort of turn off the entries of A squared that, that look like this, where I and j can't be in any triangle simply because they're not connected to each other. That multiplication by aij, will kill this. But if ij are connected to each other, then this will be 1, and this will count the number of k such that this picture is valid. Okay, and so that's how the fastest known algorithm for counting triangles works. Is it applies matrix multiplication to square the adjacency matrix, and then once you have that squared adjacency matrix, it's kind of trivial in linear time to count the number of triangles. Okay, so discussing this problem does require me to spend 15 minutes talking about just forget interactive proofs. Here are known algorithms for this triangle counting problem. But once we spend that 15 minutes, this becomes a very clean and interesting application of the SumCheck protocol to convey why it's so powerful and how you use it to solve problems that are not obviously solvable, expressible in the form that the SumCheck protocol is useful for, a sum of evaluations of some efficiently evaluable polynomial. Okay, any questions about this algorithm that goes through matrix multiplication?
Not seeing any in the chat.
Okay, great. All right, so let's use the SumCheck protocol to give an interactive proof to solve this problem. Okay, so the main thing, as in really any application of the SumCheck protocol, that you have to get comfortable with is interpreting, vectors or matrices not as vectors and matrices, but rather as functions over 0, 1 to the L, for an appropriate L. This is the thing that is very weird for people until you get used to it. So this adjacency matrix A, maybe I'll take the example from above and copy it down. Right, it's a 4x4 matrix, so it has 16 entries. Okay, but we don't want to think of it as a vector of length 16 or a 4x4 matrix. Really, what we want to interpret it. Sorry, let me. Looks like my iPad's going to die if I don't plug it in, and I tend to forget. So let me just plug it in right now. So we don't want to interpret it as a 4x4 matrix. We want to interpret it as a function whose domain is the Boolean hypercube 0, 1 to the L. And we're just going to, it's very to get used to it. So we're going to interpret it as I'm going to abuse notation here. Now the pink A is going to be a function on whose domain is 0, 1 to the 4, right? And so the size of this domain, so there are 16, elements of this domain. Okay. Sometimes the pen operates funny, and when things are plugged in, how annoying. All right, I'll unplug it again for a moment. Yeah. So, I chose this domain so that the size of the domain matches the number of entries of the matrix. And that way we can interpret the matrix as just listing the evaluations of the function. So that is, we're going to say that A of 0, 0, 0, 0 is the top left entry of A, of blue A. A of 0, 0, 0, 1 is the next entry. A of 0, 0, 1, 0 is the next entry. A of 0, 0, 1, 1 is the next entry. Oop, that's one. I won't do all 16 because hopefully you get the idea and you'll just get bored. But A of 0, 1, 0, 0 is the next entry, and so forth. So again, we interpret our matrix that has 16 entries instead as a function whose domain is 0, 1 to the L, where L is chosen so that the size of the domain is the same as 16, the number of entries in the matrix. Okay, and the reason we do that is once you have any function over 0, 1 to the L, it makes sense to talk about its multilinear extension polynomial. So, it's uniquely defined, be the unique multilinear extension polynomial, MLE of A. Good. So that, this is why we want to interpret the matrix A instead as a function over this domain, is so that we can, talk about this multilinear polynomial, because the sum check protocol needs a polynomial to apply the sum check protocol to. Okay. Any questions about this correspondence between the matrix A and, ultimately this multilinear polynomial A twiddle?
Yeah, I've invited a couple people to speak. One from Nicholas is this the same we did in Spartan for the R1 CS matrices?
Yes, exactly. So, Spartan involves, the sum check involves both some vectors and some matrices, and this would be the same A twiddle from for the matrices in that protocol. That's exactly right.
I wanted to ask, you started this part with the notion of viewing of vectors and matrices as a polynomial, as a multilinear polynomial, and I just wanted to understand if you are talking about vectors and matrices of binary values, or any value can be translated to this.
Yeah, great question. So any values work. So, I defined the counting triangles problem to only consider graphs, where edges do not have a weight, which means if the edge is not there, it's like its weight is 0, and if the edge is there, its weight is 1. And that's why this A has 0s and 1s. But you could define a notion of counting triangles with weighted graphs, where each edge that is there has a weight. So, maybe this edge has weight 2. If you want to keep things undirected, then this would also be weight 2. Maybe maybe I don't know, this edge has weight 7. And to keep things undirected, there'd be, this is what, 2, 3, so 3, 2. Sorry, this is row 3, column 2. So row 2, column 3 would also then be a 7. This, transposing matrices is far too complicated for me to handle right now. And then this would all still work. And all that matters is that the entries of the matrix are in a field, are in some field. And then there's one more nuisance, well, we haven't quite gotten to the nuisance yet, but which I'll flag in a second. But so I'm about to give you an expression. So in a moment, I will write down an expression for the number of triangles in the graph in terms of this polynomial a twiddle. And this expression will only make sense. So I'll write it down in a moment, assuming the field is big enough. So the field size, or the field characteristic, actually, is what's important. Field characteristic. If you don't know what a field characteristic is, don't worry about it right now. Is at least the number of triangles in the graph. Number of triangles in the graph. So big enough. Yeah. So in general, as we'll see, like the sum check protocol is going to wind up computing a big sum of evaluations of some polynomial, which I'm about to write down. And that sum is going to be defined over, this field, the field that a twiddle is defined over. And so as long as it kind of makes sense to, interpret the actual input to the problem, this matrix blue A, the entries of that input as coming from a field, everything's great. Because you can take, regardless of what field or domain the entries of the matrix A live in, you can always interpret the domain of A viewed as a function as 0, 1 to the L for an appropriate L. And all that matters is, again, that the entries of the matrix live in the field, because ultimately this multilinear extension has to be over that field. Was that a clear enough answer? Sorry, I was rambling.
I see no protest. Looks good.
Okay, great. Yeah, so the one sentence answer is it's not important at all that the entries of the matrix blue A are 0, 1. As long as they're field elements, then it makes sense to talk about this multilinear polynomial here over the field. Okay. So now that I've defined this multilinear polynomial, then it turns out the number of triangles in the graph is equal to the following. So the sum over all I, J, K, each in 0, 1 to the log n, log base 2 of n. Remember, n is the number of nodes. So you think of I, J, and K as like we're assigning a binary label now to each node, a log n bit label. Because there are n nodes, we can assign each of the n nodes a unique log n bit label. And the number of triangles in the graph is the same as, summing over ijk of a twiddle I comma j times a twiddle j comma k times a twiddle I comma k. Okay, and this is the exact same sum I wrote here. So it's the same sum from before. Okay, it's just when I wrote the sum here, like we had no notion of a polynomial whose evaluations were being summed. We just had the input entries of the input being summed. But here we actually have a polynomial now. So so let G be the 3 log n variate polynomial such that G of I comma j comma k, where each of these 3 things are log n variables. Defined as what's being summed here. So a twiddle I comma j times a twiddle j comma k times a twiddle I comma k. Okay, so we can just apply sum check to G. this will compute this expression here. Let me call it star. Okay, that's it. You know, at the end of sum check, the verifier needs to evaluate G of R. Let me call it R1, R2, R3, where each of these three, you know, R1, R2, R3 is each in field to the log n. And, you know, this entails evaluating a twiddle at R1, R2, a twiddle at R2, R3, and a twiddle at R1, R3. Okay. And each of these three evaluations, the verifier can compute on its own using multilinear Lagrange interpolation in n squared time. Okay, so I mean, that is the protocol. So I covered that very quickly. So let me kind of say it again, right? So what this is doing, this expression star here, is, you know, it's summing over all triples of nodes, you know, now each node being identified by a binary string, you know, with log n bits rather than like a number between 1 and n. You know, sum check always sums over, you know, binary strings. And, you know, ascertaining whether or not that triple of nodes forms a triangle. And then this sum is just done, you know, this sum is like a sum in the field. And so this is why I was saying that, you know, my claim that this expression equals the number of triangles in the graph sort of assumes that there's not some kind of wraparound issue whereby summing in the field does something different than summing over the integers, right? So if there are like, you know, 1,015 triangles in the graph, and you work over a field of characteristic, you know, 2, you know, then this sum will sort of actually compute the number of triangles mod 2 rather than the actual number of triangles. But if you work over a big, you know, a large prime order field, then, you know, this sum in the field sort of behaves identically to doing the sum over the integers. And then, like, you know, getting out the sum as a field element is kind of the same as telling you the number of triangles as an integer. Yeah, so let me just pause there. I mean, that is the protocol. Like, you just apply sum check to this 3 log n varied polynomial G. And here again, you see this thing that I think is pretty confusing till you get used to it, where G is not multilinear, right? G is degree 2. G is degree 2 in each variable, right? But it's obtained by, it's built out of a multilinear thing, right? So a twiddle is multilinear, but G, you know, takes variables I, J, and K, and it feeds I into a twiddle, you know, twice. And that's why G itself is not multilinear, even though a twiddle is. Okay. And, you know, as I've explained, as I mentioned before, like, we basically never apply sum check to an actual multilinear thing. What we typically do is we apply sum check to a non-multilinear thing that's somehow built out of multilinear things. And the fact that we're building it out of multilinear things is useful both to the verifier and the prover. As I've discussed here, you know, the verifier can evaluate the multilinear thing at any desired point in linear time. And that's what ensures that the verifier at the, you know, in the sum check protocol is linear time. I haven't really discussed prover time yet for this. But that's it. So the protocol is literally just apply the sum check protocol to this, you know, 3 log n varied polynomial, which has degree 2 in each variable. You know, the protocol has 1 round per variable, so that's 3 log n rounds. And in each round, the prover sends a degree 2 univariate polynomial, you know, so the total proof length across all the rounds is something like it's 3 field elements per round, 3 log n rounds, so it's like 9 log base 2 of n field elements. Yeah, so that's it. That's the protocol. Okay. Any questions?
Hey, Justin. So if I like right now, you said something about this, but I'm a bit confused on something. In each round, because when we saw the Samchak protocol, the challenges were like randomly sampled from the field.
Mhm.
But here you say that there are 3 log-n rounds. So
Mhm.
I'm confused if the random challenges are like built to the log-n. So if there are only 3 rounds or 3 log-n rounds. It's 3 log-n
Yes.
rounds, right?
Yeah, there are 3 log n rounds. Yeah. So what's
Okay.
happening is, so at the end of the protocol, the verifier winds up having to evaluate G at a random point. That point, which I've written here as R1, R2, R3, that R1, R2, R3, all together live in field of the 3 log n. R1, R2, R3 individually, like R1 lives in field of the log n, R2 lives in field of the log n, R3 lives in field of the log n. And so each coordinate of R1, R2, R3 there's one round devoted to that coordinate, right? So actually let me see if I can do a little example or something. I'm not going to do the whole. So I guess here we have 4 nodes. So the protocol would index the nodes as like 0, 0, 0, 1, 1, 0, 1, 1. Okay, and actually, maybe it's worth me doing the whole example. So the matrix here would be, so it's a 4x4 matrix. All right, maybe that'll get a little big. Maybe that'll get a little annoying. So maybe I don't want to do the whole example. Yeah, sorry. I'm going to bail out of this example. But G here would be 6 variate. So like x1, x2, x3, x4, x5, x6, right? And you would sort of think of these 2 variables. If everything, if you feed in 0, 1s into this, like these 2 variables would specify like the first node in the triangle. These 2 nodes would, or these 2 variables would specify the second node in the triangle, and these 2 nodes would specify, the third node in the potential triangle. And so this would be, so G would be a twiddle of x1 comma x2 comma x3 comma x4 times a twiddle of x3 comma x4 times comma x5 comma x6, times a twiddle of x1 comma x2 comma x5 comma x6. Yeah, and then so when you apply sum check to compute, the sum over in each of these individually in 0, 1, right? Like in round 1, at the end of round 1, x1 gets bound to a random value. I call it R1 prime to distinguish it from what I was calling R1 before, which is like a vector of log n random values. So in round 2, x2 gets bound to an R2 prime. In round 3, x3 gets bound to an R3 prime, and there are 6 rounds. In round 6, at the end of round 6, x6 gets bound to an x6 prime. And so the verifier has to evaluate, R6 prime. At the very end of the protocol, G of R1 prime, R2 prime, R3 prime, up to R6 prime. Yeah, so there's, if you have a 4-node graph, it takes 2 bits to index each node, which means there'll be 6 rounds of this protocol, so the first 2 rounds sort of together kind of get rid of the first of the 3 nodes in the triangle. The next 2 rounds kind of get rid of the second node in the triangle, and the final 2 rounds kind of get rid of the third node in the triangle. Was that clarifying? Did that help?
Looks like yes, so.
Okay. Yeah, great question. Whenever I cover this, I do a confusing job, and people do often think that when I write something like this, people often think that like R1 is one field element. No, in fact, it's log n field elements. And so there in total there are 3 log n rounds with like kind of the first log n sort of telling you what R1 is one round at one entry at a time. The second log n telling you what R2 is one entry at a time, and the final log n round telling you what R3 is one entry at a time.
So I also brought Skaunov on stage. I keep poking you to try and write out questions, but I think you might have one.
Okay.
to say.
Thank you for bringing me to the stage. Considering writing, it's not always possible since mobile phone and since following
Understandable.
the
Anyway,
lecture
yeah.
itself, it gets messy sometimes. My actual question, which I had, was answered during answering the last question, and but I got another one which might be better suited for the end of the lecture. It touches if it's possible to uh, map these 2 techniques that we have here on the hand, this multilinear extension, and then this sum technique of each variable scratching out. If it's possible to map this to summing and multiplying in the constraint system, or are they absolutely disjoint? But it's a little bit general question, which may be more suitable to the end.
Yeah, let me
Thanks
push that
very
to
much.
the end. Yeah, I think the general ideas and ethos of this application of the SumCheck protocol is like identical to the situation when you have, you want to give like a snark for general constraint systems. But the details might be a little different because, stuff in the snark some of the stuff is committed and things like that. So let me just defer a little bit, since my main goal today is just to see like several applications of SumCheck, just to get used to, how we wind up using it, how we kind of turn problems that don't on their face involve summing up all evaluations of some polynomial and then turn the problem into that form. Okay. Other questions right now?
I'm trying to get Nicholas to join us. You should see an invite, Nicholas. But he's asking, how will the cost change if we consider a larger product set as a base for the SumCheck protocol, i.e. the set of 1 to n squared instead of 1 to the log n, and to retrieve more natural labeling matrix and entries?
Yeah, great. Yeah, so the SumCheck protocol does apply, like, it will compute, sum over, like, if you have an n-variate polynomial G. Sorry, let me write this out. My answer to this in the end will be quick, but let me, n-variate polynomial G. The SumCheck protocol can compute the sum over all x in any product set, so h to the n for any h a subset of the field of g of x. Okay, and so, a natural thing to do for this counting triangles thing is to let h be like the set of all nodes in the graph. And then what g winds up being, then a twiddle of x comma y, I really shouldn't use maybe a hat, winds up being a bivariate polynomial, so 2 variables of degree n minus 1 in each variable. Okay, and the relevant g here would now take in exactly 3 variables. Let me just call them a, b, c, and spit out a hat of little a comma little b times a hat of little b comma little c times a hat of little a comma little c. And you apply sum check, to now n is 3. This n is not the number of let me say L instead of n here. Now this L it's a 3-variate polynomial. Okay, so there are a couple issues here. So we reduced the number of rounds from 3 log n all the way down to just 3. So we got a really big improvement in the number of rounds. The big downside is that G now has degree n minus 1 in each variable instead of degree 2 in each variable. Sorry, it's 2 times n minus 1. So this G has degree 2 times n minus 1 in each of its 3 variables. So while there are only 3 rounds, the proof size per round is now like n field elements. So our proof size actually went up dramatically to something like 6n-ish field elements. 3 rounds, and in each round the prover is sending a univariate polynomial of degree like 2n minus 1 or whatever. So the proof size got much bigger. And also I'd have to think about it, but it's possible that the prover gets much slower. I'd have to think about it more, maybe. And the verifier, I think the verifier still runs in linear time, I think. It has to now evaluate this 3-variate polynomial at a point, which I think it can do in order n squared time. But it's possible now it needs more space. Anyway, that's, you got to think a little bit about what happens when, the degree in each variable of G gets so big. But, high level, the obvious things are the number of rounds falls dramatically all the way down to 3 from 3 log n, but the proof size actually grows dramatically from, 9 log n field elements up to 6n. So like exponentially bigger proof or whatever. Does that make sense?
It does to me. I think Nicholas is able to join. He might have follow-up.
Okay.
Although you're muted if you're talking, Nicholas.
Can you hear me now?
Yep.
Perfect. Yeah, I just wanted to say that the answer makes perfect sense. I was just considering only the verifier codes. That's why I didn't see the other points. Thank you very much.
Okay. Great. Yeah, thanks for the question. Yeah. So in general, like using multilinear things tends to be, the best thing for minimizing like proof size, but it does give you a lot of rounds, log n rounds. And yeah, generally multilinear things are very nice for both the prover and the verifier. But like things get complicated, can get complicated too. So yeah, but just minimizing total proof size across all the rounds, it kind of tends to make sense to have the maximum number of variables, maximum number of rounds, minimal like message length in each of the rounds, and that sort of is best for minimizing the total proof length. Sort of make each round as small as possible, have a lot of rounds. Okay, other questions?
I think that's it for now.
Great. Okay, so let's talk about matrix multiplication. All right. So this gets a little tricky to talk about as well, just because we've actually already seen a protocol for matrix multiplication, which did not use sum check. So we already saw Frivold's algorithm. Okay, and in a sense, Frivold's algorithm is kind of the best you can hope to do, as I'll explain by reminding you what it does. So here, if you have 2 input matrices, A and B, say they're both n by n, so they're both in field of the n by n. Then Frivold's algorithm will have the prover just send the claimed product matrix. So send C, which is claimed to equal A times B to the verifier. Okay, and the verifier, say, picks a random vector, R in field of the n, put an arrow over it, I guess, and confirms, C times R equals A times B times R. And this, as far as the verifier goes, the verifier does 3 matrix vector products. So that's each of those 3 matrix vector products runs in time, order n squared, and so that's up to a constant factor, n squared time for the verifier. Okay, and so we saw this algorithm probably a month ago now or something, and it's complete, it's sound, and it's really nice because the prover just sent the claimed answer and that was it. And the verifier runs in linear time, which is the best you can hope for because the verifier has to at least know what the input is. And so provers as fast as possible, in a sense. Verifiers as fast as possible, in a sense. And how could the proof be any shorter if the verifier really intends to learn the product matrix? You just can't hope to do any better, right? But in fact, you can hope to do better in certain contexts, and counting triangles is one of those contexts. This is why I described like the best known algorithm for matrix multiplication, how it works before. What this algorithm did was it took the adjacency matrix of the input graph A and it squared it. It multiplied A by itself, A by A. It squared it. Okay, but it didn't. The verifier, that does not care about A squared. It doesn't care about the n squared entries of A squared. Right. This algorithm computed A squared only as like a means to an end, not as an end in itself. Once the algorithm knew A squared, it just took linear time to get the number of triangles in the graph. Right. But like in the end, all it cared about was one number, this number in this box here. It didn't actually care about A squared. Right. So you could use Frivold's algorithm to give, it would be a non-interactive proof. There's no interaction for counting triangles, where the prover just sends A squared, or the claim value of A squared. The verifier applies Frivold's algorithm to sort of confirm with high confidence that the prover actually did send A squared and not some other matrix. And then, given A squared, the verifier on its own can very quickly in linear time compute the number of triangles. Okay, the problem with that, right, is the proof is huge now. I mean, the prover had to send A squared, and the verifier didn't care about A squared, right? So intrinsically, there's no requirement that the prover send A squared, right? So we have a non-interactive proof here using Frivold's algorithm that, the prover is like as fast as running the fastest known algorithm. The verifier is linear time, which is the fastest you can hope for. That all sounds great. The big problem is the proof is huge, right? The proof is n squared field elements, all entries of A squared. Okay, that's where you can hope to do better than Frivold's algorithm. If you don't actually care about the product matrix, there's no necessity of sending that product matrix to the verifier. Okay, so now I'm going to explain how you can use the sum check protocol to avoid sending that product matrix to the verifier. But before I talk about counting triangles again, I need to talk about matrix multiplication.
I think we had one clarifying question, actually.
Great. Please, go ahead.
Yeah, sorry, I may be missing something, but when you say it's linear in the sum of the pairs of ij, why do you say it's linear? In n, isn't it n squared?
Yeah, sorry. It's when I say linear time for, like the counting triangles problem, I mean linear in n squared.
Yeah.
Yeah.
Okay, yeah, okay. It's just, yes. Perfect.
Yeah, so it's just, linear is vague. It's annoying to have matrices and talk about linear time because it's, the size of the matrix is n squared, so linear time means n squared.
Oh, perfect. Thanks.
Yeah. Okay. Great. So let's for a moment let's imagine the prover, sends, the claimed product matrix to the verifier. But again, in applications like decounting triangles, this will not happen. It's just going to make it easier to describe the protocol. Okay. And so, yeah, so imagine the prover starts by sending the claimed product matrix to the verifier. Now here's a fact. Actually, what I want to say here. Let's say I should have stated this fact before I stated. Forget what I wrote here yet. I'm just gonna state an algebraic fact first. Okay, so let D actually equal the true product matrix. Okay, so this is an n by n matrix, but as usual, we're going to think of it as a function on 2 log n bits, so that we can talk about its multilinear extension. So let D twiddle be the multilinear extension of D, and similarly A twiddle B twiddle be the multilinear extensions of A and B. Okay, so here's the fact. I'll say so D twiddle of R1 comma R2, and again, this notation confuses people a lot, but here each of these are in field of the log n. So D twiddle is a 2 log n variate polynomial, multilinear polynomial. And so, R1, R2 is just like any input to D twiddle, 2 log n field elements. And I'm using R1 to denote like the first half of the input and R2 to denote the second half of the input. So that turns out to equal the sum over K in 0, 1 to the log n of A twiddle R1 comma K times B twiddle K comma R2. Okay. So this is just like what the right-hand side here is a really, really nice expression for the multilinear extension of the product matrix. Okay. This is the kind of expression, we've seen multiple times already. I say, hey, this multilinear extension equals this other expression. Okay. And so whenever we see such a claim, like, how do we check it? So let's check that this claim is true. So you always have to check 2 things, right? You need to check that the right-hand side is a multilinear polynomial. In R1, R2, in the thing you're feeding to the multilinear thing on the left-hand side. And then you have to check that the right-hand side and left-hand side agree at all Boolean inputs. So at all R1, R2, not in field of log n, but in 0, 1 to the log n or 2 log n. So let's check these 2 things, and if both of these things we successfully check, then we know that this equality is true, right? Because if these 2 things hold, then the left-hand side and right-hand side are the same polynomial. Yeah, because any 2 multilinear polynomials that agree at all Boolean inputs have to be the same polynomial, because the Boolean hypercube is an interpolating set for multilinear things. Okay, so the right-hand side, like checking the first bullet point, the right-hand side is clearly multilinear in R1, R2, just because A twiddle is multilinear and we feed R1 only into A twiddle, and B twiddle is multilinear and we feed R2 only into B twiddle. And so the right-hand side is clearly multilinear in R1 and R2. Great. Okay, now checking that the right-hand side and left-hand side agree at Boolean inputs. Well, if R1, R2 is Boolean, then D twiddle of R1, R2 is just like a certain entry of D of the actual product matrix. And then the fact that the right-hand side spits out the same thing just follows from the definition. So now we're talking about bullet point 2 here. Just follows, from the definition of matrix multiplication. Right. The ijth entry of the product matrix is the sum over K of AIK times BKJ. right? And that's exactly what this sum is computing. Given that A twiddle extends A and B twiddle extends B, if you feed only Boolean things into A twiddle and B twiddle, you get out exactly the associated entries of A and B. And this is just computing this sum from the definition of Major's multiplication. Okay, so that's how you see that this fact is true. Okay, so while what's going on here is while an algorithm that explicitly computes the product matrix D, the fastest known algorithm is very complicated and impractical and runs in super linear time, to explicitly compute D, right? If I only want to evaluate the multilinear extension at one point, you don't necessarily have to compute the entire product matrix. You can use the right-hand side here to get this one evaluation of D twiddle more quickly, roughly is what's going on. But right now, just take this fact as a fact, since we did just cover its proof. And now I'll tell you an interesting interactive proof for matrix multiplication. Okay, so it's a very short protocol once you take this fact as given. So I'll describe the protocol and then I'll take questions. Okay, so just imagine at the start of the protocol, the prover sent the claimed answer C. Again, in applications that will not have to happen. Okay, and say the verifier is just going to pick an R1, R2 from the whole field at random. Okay, and it's going to accept if and only if, but this is not really the end of the protocol. This is actually really just a prelude to the real protocol. So accept if and only if the multilinear extension of C at R1, R2 equals the multilinear extension of the true answer at R1, R2. And the verifier does not know this. So the verifier cannot do this check yet. So the verifier does not know D because, this is the true answer. The whole point of this protocol is to try to get the prover to tell it the true answer. The verifier does not know the true answer. What's going on here, this is just a prelude to set up the actual application of the sum check protocol. So what's going on here is if C and D are the same matrices, then C twiddle and D twiddle are the same polynomial. And of course, if you evaluate the same polynomial at the same point, this check will pass. Whereas if C is not the true answer, then C and D are not the same matrix, and hence C twiddle and D twiddle are not the same polynomial. And by Schwartz-Zippel, with overwhelming probability over the choice of R1, R2, this check will fail. Okay, so what's going on here is, checking whether this equality holds right here up to some small soundness error is equivalent to confirming that C is actually the right answer. Okay, so that was just a song and dance to reduce the original problem of making the prover, tell the verifier the product matrix, down to the task of evaluating the multilinear extension of the true product matrix at a random point. Yeah. So the key question now is how can the verifier learn D twiddle of R1, R2, where remember D is the true product matrix A times B. Okay, now finally, so this was this annoying song and dance to get us to this question. Now we're ready to to get to the real protocol. Okay, and here's the real protocol. By this fact, we have a really nice expression for D twiddle of R1, R2. Here it is. Okay, so we're just going to apply the sum check protocol to compute the right-hand side of this equality here. Okay, that's it. That's the whole protocol. So apply sum check to the log n variate degree 2 in each variable polynomial degree 2 in each variable. My pen might have died again. Just give me a second. Yeah, it died. Sorry. So let me just write this out. And it said in each variable polynomial G of maybe I call it R3 equals a twiddle of R1 comma R3 times b twiddle of R3 comma R2. Yeah, because that will give you applying sum check to this G computes the sum over z in 0, 1 to the log n of G of z, which by definition of G is a twiddle of R1 comma z times b twiddle of z comma R2, which was exactly d twiddle of R1 comma R2 by the facts above. Yeah. So So what's going on is the verifier, if the verifier wants to evaluate the multilinear extension of the actual product matrix at a single random point, it does not have to compute the actual product matrix on its own. It can just apply the sum check protocol to this particular G, and thereby force the prover to give it the evaluation of d twiddle that it needed. Okay, and at the end of sum check, okay, the verifier needs to compute G of R3 for a random R3, but that's just a twiddle of R1 comma R3 times b twiddle of R3 comma R2, and the verifier can get this can get each of these in order in linear time, for each of them by multilinear Lagrange interpolation. Okay, so that's the protocol. Okay, so to summarize, through some simple application of Schwartz-Zippel, confirming that the prover sent the correct answer reduces to evaluating the true product matrix at a single point, the multilinear extension of it at a single point in the big field. And then using the sum check protocol, the verifier can force the prover to tell it that evaluation. And at the end of that sum check protocol, the verifier just has to evaluate the multilinear extension of the input matrices, each at one point. And it can get those evaluations in linear time by multilinear Lagrange interpolation. Okay, so that is the protocol. And again, because I framed it here as the prover begins by sending the claimed product matrix, it really has no benefits over free vaults. Okay, but I will explain momentarily how to use this kind of as a subroutine in counting triangles, and then we will see a major benefit over Freevault's algorithm. And then that'll be it for today. I'm not going to do that small space, interactive proof for small space stuff because I've been taking a ton of time. So let me pause here and see if anyone wants to ask any question.
Not see any in the queue so far. Feel free to request to speak, anybody. Looks like we don't have any for now.
Okay, great. All right, so before I tell you, so we've seen an interactive proof for counting triangles already, and I'm going to give you another one that's actually much better. Okay, so why is the first one not amazing? Remember, so the first one was apply sum check to compute sum over I, j, k in 0, 1 to the 3 log n of g of I, j, k, where g was a twiddle ij times a twiddle jk times a twiddle kj, or sorry, ik. Sorry. And this was actually, it was really good for the verifier, right? There were 3 log n rounds, degree 2 univariate polynomials sent in each round. So, 3 field elements sent in each round. And the runtime of the verifier was dominated by evaluating a twiddle at 3 points, which, by multilinear Lagrange interpolation, it can do an order n squared time for the verifier. So the verifier costs of this were really good. I didn't really talk about prover costs. Okay. But it turns out that the prover cost is like n cubed time. I won't go into the details, but like basically, even this sum is over n cubed terms, right? Right. It's effectively over triples of vertices, and there are n vertices. So, the number of triples of n vertices is n cubed. Okay. And it turns out that like you can implement the sum check prover in time that's only like a constant factor slower than just like computing this sum directly. But still there are n cubed terms here. So that's n cubed time. Okay. And now like that's not terrible because this matches like the naive, the runtime of the naive algorithm for matrix, for counting triangles, up to a constant factor. So, if that algorithm were optimal, then this prover time would be, itself kind of optimal up to constant factor because the prover has to at least solve the problem. But that algorithm is not optimal, right? There's a faster algorithm based on matrix multiplication, right? And so you can hope to do better. So, can we get P to run in, order matrix multiplication time? That is just a constant factor slower than the fastest known algorithm for solving the problem? And the answer is yes. Okay, but to do that, we need the interactive proof for matrix multiplication. Okay, and by the way, we want this to happen with order log n size proofs because with Frivold's algorithm, we could achieve this. So, like this is, I already explained, like you can do this with Frivold. So can achieve this with Frivold's. Okay, just by having the prover send the claims, squared adjacency matrix, by having P send a squared, and having the verifier like apply Frivold to check that a squared is correct. But the problem with that is the proof is order n squared size, which is, horrible. So can we achieve the same, effectively the same runtime for the prover up to constant factor, but with the proof size being logarithmic instead of, log n instead of n squared? And the answer is yes. Okay, and here's how. Okay, so it's actually going to take two sum checks. So first, apply sum check to the following two log n variate polynomial. I guess I'll call it G, maybe I'll call it H, where H has degree 2 in each variable. So here it is. Maybe I'll let B be the matrix A squared. So the squared adjacency matrix. Okay, so the polynomial H of I comma J, where these are each log n variables. I'll define to be Bij times Aij. Right. And so there were, I covered this fact when I covered the fastest known algorithm for counting triangles. Let me just bring it up again. Here it was. So I probably don't want to try to copy this down because I always do a terrible job of that. But, so here's the number of triangles equals exactly this sum here. So reminder, here's the fact. I'm too incompetent to copy it down, so just bear with me. So by that fact that I just reminded you of, the sum over all nodes ij of hij is the number of triangles in the graph, right? So you apply sum check to H. Oh, sorry. So I meant to stick tildes here. Sorry. Otherwise, without the tildes, you know, this and this are not polynomials. You need the tildes there to say, hey, you know, it's not a matrix. It's just a matrix. It's actually a multilinear polynomial. So this is H. And so by the fact above, you know, that I had scrolled up to remind you, you know, summing up over the Boolean hypercube, all evaluations of H gives you the number of triangles in the graph, right? This is like kind of more or less emulating that best known algorithm for matrix multiplication, where you compute the squared adjacency matrix, and then given the squared adjacency matrix, it's, you know, this sum gives you the number of triangles. Okay, so great. So we applied sum check once, and I'll explain the prover time shortly. You know, the verifier costs are all like logarithmic here, because, you know, H has degree 2 in each variable, and there's 2 log n variables. So the big problem is that at the end of the sum check protocol, the verifier has to evaluate H at a random point. So let me call it H of R1 comma R2 for R1, R2 chosen at random from the whole field over the course of the, you know, entry by entry over the rounds of the sum check protocol. Okay, and that requires, you know, remember H of R1, R2 is B twiddle of R1, R2 times A twiddle of R1, R2. Okay, now the verifier can compute this evaluation of A twiddle on its own in linear time, so n squared time, by multilinear Lagrange interpolation. Okay, the problem is the verifier does not know B, because B is the square, you know, A squared, right? Like computing A squared is, you know, once you know A squared, you can solve counting triangles like really quickly, right? So like if the verifier had to compute A squared on its own, it might as well ignore the prover at that point and just solve the problem on its own, right? So getting this evaluation of B twiddle where B equals A squared is a problem. Okay, but that's exactly why we brought in the MATMOD protocol, right? So you can, you know, apply the MATMOD, the matrix multiplication IP, interactive proof, to compute. I mean, it, like I described it literally, you know, it solved this problem, right? You know, to compute the multilinear, you know, to compute B twiddle of R1, R2. Like it's just apply the matrix multiplication protocol from before, you know, where, you know, to the, you know, so there, I guess I shouldn't have used B, because there, yeah. Let me call the, let me switch over. Sorry, let's say this is F. So switch all, so F is A squared. The verifier does not know F, so it cannot on its own compute the multilinear extension of F at a random point. But the, you know, the matrix multiplication protocol exactly let the verifier force the prover to tell it the multilinear extension of a product matrix at a point. Where here the two matrices being producted to get F are just, you know, A both times. So, you know, in the matrix multiplication protocol, like, you know, for A times B, we just have, you know, A be the A here and B also be the A here. Yeah, and so at the end of that protocol, at the end of that sum check, the verifier needs to know needs to compute, you know, a twiddle at you know, some R1 comma R3, and a twiddle at R3 comma R1. Again, like there were two different matrices A and B, but here like B is the same as A, and so yeah. and the verifier can, compute both of those evaluations in n squared time, in linear time, by multilinear Lagrange interpolation. Okay, so I don't know if I described the protocol like that clearly, but to summarize, rather than there just being one sum check, where you compute a sum over n cubed terms, as that led to n cubed prover time, which we weren't happy with. Instead, we're going to do two sum checks, where the first sum check involves a polynomial defined, involving a product of two multilinear things, where one of the multilinear things is actually the multilinear extension of the squared adjacency matrix, which the verifier doesn't know. So at the end of that first sum check, the verifier has to evaluate that multilinear extension at a random point, but it can't do it on its own. But fortunately, we can use a second application of the sum check protocol to force the prover to give the verifier that evaluation. At the end of that second sum check, the verifier is left with some evaluations it can do on its own. Okay, and that's it. And then it turns out that the prover in the first sum check, once it knows the squared adjacency matrix, which it had to compute anyway to run the fastest known algorithm, runs in order n squared time. And the prover in the second sum check also runs in n squared time. Right, which means, all of the overhead here for the prover for proving correctness of the right answer is actually low order compared to running the fastest known algorithm, right? The most expensive thing the prover ever does is figure out what the squared adjacency matrix is. Everything else is like really, really like negligible cost. This takes, way more than n squared time, and everything else the prover does just takes n squared time. So this is what I call, this is sort of my own terminology, but I call this a super efficient interactive proof, right? The prover runs the fastest known algorithm for the problem and does a low order amount of extra work, like basically negligible, like you basically get the proof for free. Does a low order amount of extra work to prove correctness. The verifier runs in linear time, which is the best you can hope for, linear in the size of the input. So here that means n squared time because the input has size n squared. And the proof size is logarithmic. Okay. And so, you're effectively getting a rigorous guarantee that the prover correctly computed the number of triangles in the graph. The proof is basically free, right? The prover, the extra time the prover spent is negligible compared to just running the fastest known algorithm to solve the problem. The verifier just reads the input and the proof size is logarithmic. Like you just can't hope to do better than that. And so I think this is like a nice application to see. It's a little annoying because you have to talk about the counting triangles problem, which many people haven't seen before and smart people don't care about. And you have to talk about the fastest known algorithm for that problem and stuff. But nonetheless, it's a very clean application of the sum check protocol. And it sort of, it's good to see how, interaction here is giving us something better than Frivold's. Frivold's on its face seems impossible to beat because if the prover actually does have to send the product matrix to the verifier, you can't hope to beat Frivold's. But in counting triangles, there's a product matrix arising that the verifier doesn't actually care about. And so that's the situation where interactive proofs, rather than Frivold's being non-interactive, the interactive proofs can be better. So hope this was helpful. Questions?
Cool. I think you had one.
Hi, yeah, I had a question.
Mhm.
So in this case, you basically, I don't know if this abstraction is right, but you basically like replaced a sum check on a product of three polynomials with two sum checks,
Mhm.
one on a product of two polynomials and like one polynomial. So
Mhm.
the question is this like a strategy that you can generalize? Like, will it always be more efficient to break things up like this and then do multiple sum checks? than to do a sum check on a bigger thing?
Yeah, that's a really good question. I think the answer is probably yes. Probably yes. Let's see. Yes, as long as it's possible. So the first sum check involved um two things, right? Like a squared and a. And so in general, if you had like, well, yeah, let's just stick with that setting here. And I guess something that we kind of exploited, like everything was really nice for the prover once it had a squared. Okay, so the reason we kind of get super efficiency is both because I guess you could phrase it one of two ways. The fastest known algorithm for the problem has to compute a squared anyway. And the reason that algorithm is so fast is because a squared has like a very interesting non-trivial algorithm, like these fast matrix multiplication algorithms. So I think the answer to your question is yes, it does work generically, as long as like the two pieces you broke things into here, like both pieces are like kind of fast for the prover to compute. Like it had to compute it anyway just to run the fastest known algorithm for the problem or something like that. Another thing I can say is, just think for a second. Yeah, I think I'll leave it as that. So I think it is a generic technique, and I think it is definitely nicer to have two sum checks both over n squared terms than one sum check over n cubed terms. But there are definitely settings you could come up with where in the end the prover runs an n cubed time anyway. Say because if the naive algorithm for matrix multiplication were optimal, the n cube time algorithm, then this wouldn't really be helpful because it take cubic time to compute a squared, and so whatever that first the prover needs to know a squared to run that first sum check. Does that make sense?
Yeah, that makes sense. And like as a quick follow-up, so if you're trying to do 4 cycles, the super efficient way would be like break it up into a square times a square.
I think so. Yeah, and then yeah, and I'm just speculating that the fastest known algorithm to count like 4 cycles would be the natural thing that does that. That computes a squared and then like figures out the 4 cycles given a squared. And exactly what you said would be the super efficient way to prove you sort of ran that algorithm correctly, more or less. Yeah, so I think you have the key ideas down. Yeah.
Okay, thanks.
Yeah. And so again, the high level thing is like generally better to have two sums over and fewer terms rather than one sum over way more terms. But whether or not you really avoid summing over the giant number of terms, and you just pushing the problem like elsewhere in the protocol might be context dependent. Yeah, I think you see stuff like this a decent amount, like in Spartans, which we've kind of discussed, although I might cover it kind of again or something related to it again. The naive thing to do, because it involves n by n matrices, like the very naive thing to do, I guess, would involve one sum check over n squared terms if they're n by n matrices. Instead, what Spartan does is it applies two sum checks over n terms each. And so I think you're sort of seeing the same kind of thing again. It's much better to have two sum checks over n terms each than one sum check over n squared terms. And I'm hiding a lot of details here, but I think it's the right idea. Other questions?
Not seeing any at the moment. Oh, actually, yes, we do have potentially one. Duck Yeah, there it is. You're muted if you're trying to ask anything.
Oh, I'm sorry. I was asking with the well being muted. Uh, is it correct? Would it be correct to say that uh, with these two examples, you found a particular case where you could fold one proof into another proof? So it's folding, but not universal.
I guess you could sort of view it that way. This term folding is overloaded, and most of the time, well, often people use it to refer to like techniques involving snark recursion, and there's no recursion here. Recursion is like when you take a snark verifier and turn it into a circuit, and then prove you like evaluated that circuit, correctly. That's how you prove you like check the proof or something like that. And yeah, so many times when people say folding, they're referring to some kind of recursive, snark recursion technique like that. Although sometimes they use it more generally. And so, in the more general sense, I guess you could view things that way. It's sort of like, but I would just say it's like iterative application of SumCheck. So it's like we used one application to SumCheck where the application was really, really efficient because, if the prover knew the product matrix, it could run that first application to SumCheck in linear time. And at the end of, the point of that SumCheck didn't completely solve the problem and we were done, right? It sort of left us with a simpler problem, but not one that the verifier could solve on its own. The verifier needed more help from the prover. And so we used a second application of SumCheck to then solve that problem. That is to reduce that problem to a problem the verifier could solve on its own very quickly. And so, I mean, that is sort of what folding does, is it, normally it's like taking multiple instances of the same problem and sort of collapsing them into a single instance of the same problem. This was more like we took one instance of a hard problem, kind of reduced it to an easier problem, but a problem that was still not solvable by the verifier on its own, and then applied SumCheck again to reduce that to a problem the verifier could solve on its own. So, yeah, I don't know. It depends how broadly you're interpreting the term folding. I think I'd say it is a little different here.
Proof would the term would wording proof reusage be better here?
I mean, I don't think of it that way. I think of it as just like iterative application of a powerful proof technique where it's not enough to apply the technique once, you have to apply it twice to get all the way down to a problem the verifier can solve on its own. I mean, what is going on here is, I mean, you can view the matrix multiplication proof as like leveraging the fact that, so like A times B, the product matrix has n squared outputs. Okay. There has n squared, there are n squared entries of the product matrix. And if you want to compute each entry individually, you sort of need time n. And I think, that's really not avoidable if you just care about one entry, like you need time n. Okay. But like the n squared outputs, there's like, they're not independent outputs. There's like a lot of overlap between them in terms of like the work that goes into, computing them. That's exactly why we have matrix multiplication algorithms that are faster than n cubed time.
Mm-hmm.
And so I think this matrix multiplication protocol, interactive proof that we're using, is just really heavily exploiting, like all of this structure, that these n squared outputs, are not totally independent, and hence you can prove statements that the statement itself involves all n squared outputs, but doesn't require the verifier to like see all the n squared outputs, and doesn't require the prover to run in time more than n squared, once it knows all the n squared outputs. I'm being very hand wavy here. We are not doing any kind of like, take a proof, prove the proof. There's none of that, and nor are we. I don't know, like so each of these n squared outputs is kind of like a related instance of the same problem. That problem being compute the inner product of two vectors, a row of A and a column of B. And so there is reuse of something happening, but I don't think it's the same kind of reuse that people normally refer to when they talk about folding. Right, so
Yeah, I see the difference in perspective now. Thank you. It's like you said, iterative approach. Something to think about. Thank you.
It's a good question. So thanks for asking it. I guess the answer is a little vague, but okay, I do have to wrap up now. So thanks for, as always, staying full 2 hours. And so actually next week I'm traveling, so it'll have to be an off week. But I think the following week will be fine, and we'll probably talk about the GKR protocol. So I look forward to covering that next time we meet. So thanks again. Talk to you soon.